Here we go. All right, 6.6. Further applications in modeling. So we're looking at more word problems and how to use them. So physical science, we use exponential equations a lot. So a of t equals a sub 0 e to the kt. So a sub 0, anytime you see that sub 0, you're talking about initial quality, something at the beginning of this thing. T is time, usually in years unless it tells you otherwise. And then your growth or decay constant just represents how fast your graph is going up. So if it's increasing, it's exponential growth. And if it's decreasing, it's exponential decay. So carbon dating, finding the age of fossils, uses this equation where K is about approximately the natural log of 2 times 1 over 5,700. So if you're trying to find when it equals 1/5 of the amount, that means we want our A of t to equal 1/5 of a sub 0 of the initial amount. So we're going to plug this in to the other equation. So we'd say 1/5 a sub 0 equals that equation. Divide by a sub 0 because it goes away. Take the natural log of both sides because we have an e here. So we rewrite it like this. This ln e is going to cancel, bringing this down as our answer. Then what they do here, divided, so multiplied by 5,700 divided by negative L over ln of 2. And then you type that in the calculator and get about, so 13,235 years. And we're talking about the age of a fossil, so that 200 years isn't such a big deal. So they'd say about 13,000. The biggest piece of this is if they were looking for 1/4 of the original amount, you would change this to 1/4. So it's just that AO and then it cancels. That's how you're going to solve those carbon dating problems. Some instances, they're going to talk about half. They want to know the half-life. So that just means you're doing half of the initial set equal to the equation. The first 2.8 hours, so this time t is in hours, we're going to take our half of the initial value, and instead of t, we're going to put 2.8. So if we solved that out, our h-naughts would cancel. We'd take the natural log of both sides, so ln of 1/2 is going to equal negative 2.8k. Divide both sides by negative 2.8k. You have ln of 1/2 over negative 2.8 equals k. That's the exact value. For approximating it, we just type it into the calculator. And k equals, or is approximately 0.248. So it's just plugging things in and going backwards and forwards with your logs and your exponents. Same thing here, just done out step by step. Okay, loudness is measured in decibels. Decibel equals 10 times the log of the intensity divided by the initial intensity. So, fan noise at a Super Bowl reached levels of 1,012 IO. Find the decibel rating. So we're plugging that in for I. That was the intensity. So 10,012 IO over IO. So these are going to cancel. We can just type that in the calculator. 10 log, 1012, and you get 10 log 1012. You get 30.1, so it has 30 decibels. So the Super Bowl was 30 decibels. Telephone is 80 decibels. So your phone is more intense than that fan noise. Well, I did something wrong. 10 to the 12th. Oh, okay. Well, I wrote, because of the way this was written, it didn't have the exponent. If you did it with the exponent here, 10 to the 12th, the IOs would still cancel. Type that and you get 120. That makes much more sense. 120 decibels is a lot more than 80 decibels. If we were trying to see how much more, 10 to the 12th over 10 to the 8 is 10 to the 4. So that's 10,000 times louder. That makes more sense than the answer I got. But I also used, it didn't have the exponent. So 10,000 times intense than the telephone. All right, now we're going to look at some investing. So if you remember, for compound interest, this is your formula. And this should be given to you on a test. So if I forget to give it to you, please let me know. You can use it on the quizzes and stuff. Here's our formula. So we're going to plug in. That's our principal. That's what we're putting in. This is our rate, but as a decimal, it's 0.02. Compounded quarterly, so n equals 4. And this is what our actual value is. So we're going to plug those numbers in. 2,700 equals 1,000 times 1 plus 0.02 over 4 and 4t. So we got to get the t alone. So we're going to divide everything by 1,000. So we get 2.7 equals, and if I put that in a calculator, it's 1.05. Now we got to take some logarithms. So log of both sides, log base 1.05 of 2.7 equals 4t. Using our change of base, log 2.7 over log 1.05. So remember, the base stays on the bottom. Then we're going to divide both sides by 4. So log 2.7 over log 1.05 divided by 4 would give us our time. So if we plug that in the calculator, we get 49.8. So it will take about 50 years for that $1,000 to get to 2,700. So just plugging in what you know and working backwards. Now we're doing continuously. So that's our PERT. How long will it take for the money in account to double? So if our principal is P, then doubling that is 2P. So we're going to plug those in. So we've got 2P equals PE. Our rate is 0.0125, and we have a T there. So divide both sides by P. 2 equals E to the 0.0125T. Take the natural log of both sides because of E. You get ln equals 0.0125T. Divide both sides by that. And there's your exact answer for T. If you plug that in the calculator, you get 55.45. So it takes about 55.5 years for the money to double. So realistically, exponents are used a lot when we're doing dating old things and money. Population is another time where exponents are used. This whole thing is an exponent. So if we want to know when the world population may reach 8 billion, we plug 8 in for P and solve. So we start by dividing by 7. Over 7. Then we take the log of both sides. So log base 1.01 of 8/7 equals x minus 2011. Change of base, log of 8/7 over log of 1.01. I'm going to add this to both sides. So there's our exact answer. And if we type that in the calculator, we get 2024. So that is the year that they predict the world population may reach 8 billion. Solar energy only accounts for a small percentage of the planet's electricity, but it's rapidly growing. Cells are needed to generate, and each year since 1980, the cost has been about 90% as much as the prior year. In 1980, the price was $30 per watt produced. So we can model that with this equation. X is the years after 1980. So that means X equals 0 is 1980. X equals 5 would be 1985, and so on and so forth. They want us to predict when they were 75 cents per watt. We can model the price in dollars. So we're going to plug in 0.75 over here for f of x. So 30 times 0.90 to the x equals 0.75. So divide by 30. 0.90x equals, where did I do this? Lost my place. Oh, right here. Wow. 0.025 log base 90 of 0.025 equals x. Change a base, puts the argument on top and the base on the bottom. And if you type that in the calculator, you get x equals 35. So 35 years after 1980 is 2015. So the prediction was that in 2015, they thought it would be 75 cents per watt. I think the real one was like 2013. So it was a pretty close prediction considering we're, 30 years ahead here. And then graphing calculator, you could also put the y of 0.75, put the original logarithmic equation, and then find your intersection point where you get the 35 that way. So those are some word problem examples.